Okay, I want to talk about gravitational fields, but a little bit about field theory in general. So fields are used to describe, in essence, the direction of a force on a test particle, but they kind of completely ignore the mass or the charge of the test particle. So this might be your test particle, and this might be your mass. Let's call this the Earth, for example. Your test particle could be anything, anything at all. I could pick up a calculator, this is my test particle. And what we find is that if that's the Earth and this is the test particle, the gravitational field lines should point in the direction of the force on the test particle. So in this case, the force on the test particle is towards the Earth, and you really can have any number of test particles in any direction. So the gravitational field lines should point towards the surface of the planet, meaning objects near the surface of the planet are going to feel a force towards the surface of the planet. Makes complete sense. We're going to see the same thing with electric fields and magnetic fields, except sometimes with electric fields and magnetic fields they are repulsive and might point away depending on the charge of the object, for example. But for gravitational forces, they are always attractive, so field lines will always point towards an object. There's actually a term that we can use, gravitational field strength, that tells you the strength of a gravitational field. And simply put, if you look on the reference table, it tells you right there in the list of constants, it's the letter G. G is the gravitational field strength. So when we say G is the acceleration due to a falling object, or acceleration on a falling object due to the Earth, another fancy word for it is gravitational field strength. And if you look at the units, it's going to be meters per second squared. Now sometimes you will see field strength phrased in a slightly different way. The units turn out to be the same, it's just a slightly different derivation of the units. It's going to be a force divided by a mass. So if this was your force is G, m of the Earth, mass of the test particle, divided by r squared, the distance between them, you just divide this by the mass of the test particle. Gravitational field strength depends on the planet, for example, but not the test particle. So then these two things go away, and gravitational field strength should be G, mass of the Earth, divided by r squared. And if you put numbers in for mass of the Earth and radius of the Earth, you should get 9.8 meters per second squared. If you do it for a different planet, you'll get slightly different numbers. But depending on the units, if you divide force divided by mass, because that's what you're doing, you're taking a force and you're dividing it by a mass, the units you're going to get are newtons per kilogram. And it turns out that newtons per kilogram are the exact same unit as meters per second squared. And either of those are acceptable. So that's gravitational fields. Thank you very much for watching.